Okay, is everybody ready for another beautiful day of signal to systems recitation? I am. Okay, I'm going to share my screen. Okay, everybody see it and hear me okay?
Yep, you're all good.
Okay, so really quickly, we're going to do a little recap of the steps and theory behind convolution. So just a quick recap so everybody's on the same page, and then we're going to hop into a practice problem. A little bit more challenging than last week, so you guys have um, some more examples under your belt, right? Okay, so convolution. If you guys don't remember the formula, here's the formula. So we have y of t equals x of t convoluted with h of t. And just as a reminder, guys, this is not a multiplication sign. This is a convolution sign. So this little asterisk means convolution. And we can rewrite this as the integral for continuous functions, integral of negative infinity to infinity, x of tau, h of t minus tau d tau, right? So here we have our tau, and this is our dummy variable, guys, our dummy variable. And then we have t. And this is just t for time. And guys, based on, since we're integrating with d tau, now we're integrating over tau, right? So that's now our new variable that we're integrating over. So now let's go over the steps really quick of how to solve a convolution problem. Okay. So the first step is to replace t with tau. So we have x of t, right? Let's go back up here. So we started with this x of t convoluted with h of t, right? We started with this. So the first step is to replace that t with our dummy variable tau. So replace t with tau. And, just for your knowledge, tau could be pretty much anything, just a dummy variable. You can call it whatever you want, but to be consistent and to stay with the literature of the textbook and the class, you should use tau. Okay, so we replace that with tau. And the second step is now, so we do this for x of t. So x of t becomes x of tau, and h of t, which becomes h of tau. And just as a reminder, guys, this is going to be your signal, and this is going to be your kernels. These are terms you're going to hear, so better to get familiar with them. Include it into your vocabulary, guys. Okay, so now step two. Step two is we're now going to reflect the kernel in the time domain, on the time dimension. So we're going to time reverse h of tau. So h of tau now becomes h of negative tau. Okay? Everyone feeling good so far? Please interrupt if you have any questions, okay? So after step one, we're good with x of t. All we did was change the variable. This is not altering the signal in any way, but either the signal or the kernel. We just replaced t with tau. So all we did was change the variable. It's like calling x y, right? We're just changing the name of it. So we don't actually alter the signal. So then after we just change the name of the variable, we can put a pause on messing with x of t and x of tau, and now we're going to only be messing with the kernel. So here we take h of tau and we time reverse it, right?
Hi, Will.
What's up, Rui?
Oh, when you have the points, you say signal and what's then
The other one?
signal and for h of t, what you say for that?
I'm sorry, what was your question,
Okay.
Rui? So what is this called? It's called the kernel. Is that your question? Could you say your question one more time, Rui?
Oh, what do you say for you have the signal and does that say we know?
Oh, kernel. This is a K. Kernel. So
Okay,
K
thank you.
Kernel. Yeah, kernel. So that's what
Okay.
we're gonna. So
Yeah.
we're convoluting x of t with h of t. So the thing that comes after the asterisk is your kernel. So yeah, and I'll show you visually in just 1 second. So then what we're going to do, yeah, like a popcorn kernel. I'm gonna steal that, Isabella. That's now my saying. That's Will Knowles saying. Okay, so now we are going to time shift the kernel. So we're going to now say we have our kernel and we're going to flip it in time, and then we're going to have it all the way to the left and slide it across our signal. So we're now going to time shift starting all the way to the left and slide it over. So just to actually show you guys, it's not the most beautiful demo, but here's an example, right? So let's have some arbitrary signals. So let's call this x of tau, or I guess we could just start off real quick. We could just call this x of t, and then we have this other time series signal. We'd call this h of t. Okay, so we replace time with tau. So just the variables, right? So what this looks like, guys, is literally the same exact thing, but we're just calling the variable something different, right? So now instead of t, we were just calling it tau, but the signals don't actually change, right? It's the same. It's just like you could think of it almost as a nomenclature thing, right? The signal doesn't change. And now that we've changed the variable, this guy's done. So the signal is done. Boom. Boom. Okay. And here's our kernel, guys. And now we're going to time reverse kernel. This is a K, guys.
Sorry, would you mind scrolling up a little bit? I kind of missed the first graph.
Yeah. Okay, so this is just some arbitrary time series signal that I've drawn. We could pretend that this is like, I don't know, microvolts or something, or millivolts, or anything that you're measuring, right? It could be anything you're measuring. So just some arbitrary signal I'm using for a brief example before we hop into
Yeah.
something that's has an actual function to define it. But you feeling good? Okay, guys. So now we are going to time reverse this. So what does that look like? We're just flipping it, guys. We're just flipping it. So we just flip it in time like this. Okay? We flip it in time like that. Everybody see what I just did? I'll do it one more time. So we have it and we just flip it. We're just time reversing it, guys. Okay? We just apply a time reversal transformation.
Do we flip it against the vertical axis?
you time reverse it. So yeah, you're reflecting it across the vertical axis.
Okay.
But it's a time reversal. So this would be h of minus t now, guys.
Will you technically flipped it vertically as well when you flipped it around? But you just want to flip it in time.
Yeah, that's true. Actually, that is true. That's a bad demonstration. Pretend that I only flipped it across the y-axis. Yeah, I was testing you guys. Nicholas, you passed. You get extra credit. You can tell professor I said so. I'm just joking. Yeah, so we only want to reflect it in time, guys. So let's pretend that this h of minus tau is just time reversed, okay? And now, guys, we're going to take our kernel and we're going to start it all the way over to the left like this, so that only a little, right before there's no overlap is when you're going to start it. So you're shifting it all the way before x of tau ever starts, assuming it's a time-bounded signal. And then we're going to slowly slide it across here until we get to all the way to the other side where there's no overlap on this side, assuming they're both time-bounded signals. Okay? And the reason we're doing this is we're going to try to identify areas, specifically for continuous signals, we're going to try and identify areas where there's no overlap between the signals. So something like this, or no overlap, right? There's some overlap, or they're completely overlapping, guys. So something like this, and we would slide it again until there's only partial overlap, like this, and then once again until there's no overlap. Okay? So we're trying to identify when those regions exist, and then once we identify those regions, we can go back to this formula and integrate on those bounds. For the time bounds, or I guess the tau bounds, where all of that, there's either only some overlap or only full overlap within those regions, right? Okay, so let's see. Anything that I missed, Ryan? Anything that I missed?
I think just the T shift, you explained it, but you didn't actually put the plus T.
Yeah. Right, so
And that
becomes
step
T.
will become more clear in the example I'm about to do.
Exactly. So once again, guys, we're shifting it by T. We're trying to identify the different regions where there's no overlap, some overlap, partial overlap, and there doesn't have to be, or fully overlapping. I mean, some overlap once again, and these will change, depending on whether you have a time-bounded or a time-unbounded signal. But, yeah, Ryan will have a more concrete example. So really briefly, I know I mentioned this last time, but just to hammer it down. So the reason we're actually performing convolution and how you can think of convolution, right, is that we're finding the similarity between two signals. So by doing this, we can see how much the signals are relating to each other. We can find the mapping of one onto the other. And this is useful in many applications like image processing or time series signal analysis. So this is one of the most foundational skills you're going to learn in this class. And I would definitely recommend if you're going to go all out to learn as best you can. Okay. All right. So, and this will actually produce that third signal, right? Y of t, which basically tells you how similar, you're asking the question, how similar are these two signals? So you get this third signal that kind of shows the mapping for how similar these two signals are. Okay. So practically convolution has, a lot of applications. So this is very relevant. And if you have any, you want to go over some examples in office hours or at the end of recitation for, how convolution is used, we're happy to do so. But
just
yeah.
real quick, is there like assuming both of these, the H of T and the X of T are signals coming in, right?
Is there a preference for which one you choose as the kernel and which one you choose as the signal?
So
Mm,
generally in real world application, your kernel is going to be defined by you. So
Got it.
I do image processing research, so it's all two-dimensional, but it's a similar idea. You define the kernel based off of what you want, and then you convolve that with your signal. So generally, you're not going to have both be defined as a signal.
I would say it also depends on the system. So remember how we kind of defined H of T as your impulse response? And so like in the case of image processing, yeah, you can define your own kernel and do a convolution, but for systems, I would say it's the impulse response of the system.
Yeah,
Okay.
that's also true. So that's just going to be a system dependent, basically.
right. So just adding on to that a little bit. So image processing is a huge part of signal analysis, right? And there's another portion, maybe like neural time series analysis, or just time series analysis in general of any biopotential of ECG, of EMG, muscles, heart, whatever. So we could just maybe define this as just time series analysis, right? So you guys are going to learn this a little bit later. So I don't want to go into too much detail, but basically, if a signal is periodic and stationary, we can apply the Fourier transform and we can get a bunch of different frequency, a bunch of corresponding sine waves of different amplitudes and frequencies that compose that initial signal, right? So we can break this up into different frequencies, like 2 hertz, whatever, 4 hertz, 8 hertz. We can go like 16 and 32. So we can get really slow, faster and faster. And we can break up our initial signal into all these different sine waves, right? And at least in neural engineering and like using EEG data, a lot of times these different frequencies have different cognitive, it's been shown that they represent different cognitive functions, right? And so how we actually can get that is we have this signal and our kernel is a filter, right? So we want to apply maybe a bandpass filter from, I'm not sure, maybe like 3 to 6 hertz or something. And so we convolve our initial time series data with that filter, and we can get a signal of just that frequency band, right? So you're gonna learn a lot more of that later. That's like a very brief intro, but so it has, convolution has application like they were saying, Teresa and Ryan, in image processing and also in, neural time series data.
And also kind of to answer one of the original questions, so convolutions are commutative, which basically means you can switch the x convolved with h is the same thing as h convolved with x.
Mhm.
So just FYI.
Great point. Great point. Okay. Any other questions, guys? Okay. So if you get curious about any other applications or anything, you can always type in the chat, or we can talk about it at the end, or just interrupt. Like, yeah, like you did, or yeah. But for now, let's hop into a question that might help you solve some convolution problems for the test or homework or in general. Okay. So Ryan, you want to take it from here?
Absolutely.
Okay. Let's do it.
All right. So we're going to jump into a problem. I introduced this problem in last week's recitation. So I hope for those of you that were there, you gave it a shot over the last week. But I'll go ahead and reintroduce it and then solve it now for anybody that wasn't there. So as Will said before, we want to go through these steps in a pretty linear order. I like to add a step at the beginning to just graph the functions to begin with, so I get an idea of what I'm working with. So let's graph the functions. So in this instance, we're convolving two functions together, x of t and h of t, where x of t is sine of t times u of t, and h of t is e to the minus 3t times u of t. So let's go ahead and graph those. At this point, I imagine most of you are familiar with these step functions and are comfortable with it. So for the first graph, we're just going to have a sine wave that starts at 0 and then continues on towards positive infinity in the time axis. So it's going to look, excuse my poor penmanship, but it's going to look something like that. And it's going to keep going on to the right forever. And our h of t is going to be a decaying exponential function, also starting at 0. So it's going to look something like this, carrying on to positive infinity as well. So now that we have an idea of what our functions look like, let's go ahead and swap for the dummy variable. So we're going to go ahead and swap t for tau. And that's going to give us x of tau is equal to sine of tau times u of tau. We're going to get h of tau is equal to e to the minus 3 tau u of tau. And that graph is going to look the same as the graphs in the first, except we're going to swap the t on the x-axis to be tau. And then for step 3, we're going to take a time reversal. And t shift for h of tau. So first we're going to do the time reversal. So we're going to get h of negative tau is equal to e to the minus 3 times negative tau times u of negative tau. I'm going to go ahead and graph this so you can see. So we're going to get tau on this axis. We're going to get h of negative tau. And that is just going to flip our function like so. And then we're going to shift by t. So we're going to get h of t minus tau, which is equivalent to h of negative tau plus t, if you prefer it in that form. Either form will work, but we're going to stick with the textbook one here. And we're going to get e to the minus 3 times t minus tau, u of t minus tau. And now that is going to give us a function that looks like this. So now we have our two functions. So we have h of t minus tau, and we have x of tau, which is going to look like a sine wave, starting at 0. So now I'm actually going to draw that out so we can see it easier. Sorry, that should be x of tau. So now we're going to take our h of t minus tau, and we're going to determine when those two graphs overlap. So can anybody tell me, in this case, there are going to be two different cases that we have to solve. Can anybody tell me what the parameter for those cases are?
Talking about like partial overlap and full overlap?
Yes, so we're actually in this case going to have no overlap and partial overlap. because the x of tau function goes on indefinitely, it's kind of hard to say we have full overlap ever. But you'll see as we move on how the two cases fulfill all the conditions. And yes, Isabella, so you do the two parameters for your conditions are when t is less than 0 and when t is greater than 0. So we're going to go ahead for, what step are we on? Step 4. We're going to find overlap regions. So when t is less than 0, we're going to have no overlap. Because as you can see up here, our t defines that right side of our function, and at any value of less than 0, it's not going to have any overlap with this function that starts at 0. So we can say there's no overlap. And whenever there's no overlap, we can say y of t is equal to 0. So that one's easy. That's half the problem done. So now our second case, when t is greater than 0, we have overlap. So now we're going to have to use our convolution integral. So as Will said before, our convolution integral is defined as the integral from negative infinity to infinity of x of tau times h of t minus tau, d tau. So in this case, we can substitute our functions in, and we get y of t is equal to the integral from negative infinity to infinity of sine of tau times u of tau times our h of t is going to be e to the minus 3 t minus tau u of t minus tau. So now we have our two conditions. And as I said earlier, there's not going to be a third condition where we have full overlap because that would only happen at the point of infinity. Actually, that would never happen because your h of t is unbounded on the left. So even if you took it all the way to the right infinitely, it would cover the whole graph. So you're only going to have two cases here. And one of them is already solved. So now
I think it's not quite accurate to call h of t unbounded.
No?
Because doesn't unbounded refer to like the amplitude, like the y values?
Yeah, I should say it's unbounded in the time domain.
Yeah,
Is what I should say. Sorry.
that's probably a little more accurate.
Yeah,
Yeah, because
and
it goes on to infinity, or
it specifically goes on to
yeah.
negative infinity. Yeah.
Yeah, negative infinity. Correct.
So we're going to now solve the convolution integrals. So in this case, we only have one, and we defined it up above as y of t is equal to negative infinity to infinity sine of tau times u of tau times e to the minus 3 t minus tau u of t minus tau d tau. Now we can use our step functions to bound our integral, which is going to make this a lot easier and solvable. So when we look at this, we have u of t and u of t minus tau. And I think it's easier to see it when it's graphical. So we're going to go back up here. So as we can see with our function x of tau, and as we defined in our first case down here, when t is less than 0, y of t is going to be equal to 0. So we can set that as our leftmost bound. And then we're always going to be integrating as we sweep this function across. So let's say we swept it this far across x of tau. We're always going to be integrating to this t value. So we're always going to be integrating from that axis to this t value. So that's going to be our upper bound of integration. So we can rewrite this as y of t is equal to the integral from 0 to t of sine of tau e to the minus 3 t minus tau d tau. And we can remove our step functions from the function because they're accounted for in our limits of integration.
Hey, Ryan, sorry to interrupt. Rui has
Yeah.
a question. How did you get t greater than 0 as being overlapped? I'm still kind of confused on that.
Yeah, so whenever this t value up here is what you're worried about. So let's say in this position, it's equal to minus 2, which over on this graph, I'm going to go ahead and get rid of this. Minus 2 would be here. So you would have something that looks like this, where this is your h of t minus tau, and the other function's your x of tau. So you can see there's no overlap there. But as we sweep that function across, once we get past t is equal to 0, we're going to have overlap. Technically, this should be the same height at t. So you can see here, whenever your t is greater than 0, as you sweep this across like in this direction, you're going to start getting overlap. And then our bounds are going to be this area here, where you have from 0 to t. And that's how we got our limits of integration. Does that make more sense? Did that clarify your question? Okay, perfect. And please feel free, Will. I'm not looking at the chat, so if anybody asks a question in the chat, feel free to let me know.
Gotcha. Rui's asking, do we always start with 0?
So you don't always start with 0. It all depends on what your functions are. So if your x of t up here, if this step function, your u of t value, was shifted, let's say it was shifted to the left by 1, you would start from -1 to t instead, because that's where your functions would start to overlap. Does that make sense? Okay, perfect. All right. So now we have this defined as our integral. And now there's a number of different ways to approach it. And we're going to end up taking a way that most of you have probably not done before. But if you look at this, your first guess would most likely be integration by parts. We have two functions multiplied together. First thought goes to integration by parts. But you can see, due to the nature of these two functions, you have sine of tau and e to tau. And it doesn't matter how many times you integrate or derive these, you're not going to be able to get rid of one of the functions, which is the goal of integration by parts. So we should be able to rule that out pretty quickly. So now what you have to consider, and what we reviewed in the first recitation, is something called Euler's formula. And I hope I spelled his name right. So you will need to know this, so it is worth putting to memory. But Euler's formula defines sine of t in the complex form, which is going to be e to the jt minus e to the minus jt over 2j, where j is equal to I, but in engineering notation, we generally use j. Or is it in scientific notation, we generally use j? I don't know. In whatever notation Dr. Cody Bakar would like us to use, we use j. And then cosine of t is going to be equal to e to the jt plus e to the minus jt over 2. So those are two definitions that you will need to know. So please put those to memory. And they will be posted along with this recitation, I believe. Actually, I'm not positive they're in the slides, but they will be on my work with the recitation. So feel free to consult back to this. But using Euler's formula, we can go ahead and rewrite our integral as y of t is equal to the integral from 0 to t. And then we have sine of tau. So we're going to use Euler's formula, and we're just going to substitute all of the t's for taus. And we're going to get e to the j tau minus e to the minus j tau over 2j times e to the minus 3 t minus tau d tau. Now, what we're going to do is we're going to simplify this a little bit. And we're going to leave our first term the same. And we're just going to multiply our minus 3 out. So we're going to get e to the minus 3t plus 3 tau d tau. And we can simplify this a little bit further by pulling out the 2j term, as it's just a constant. So we're going to get 1 over 2j, integral from 0 to t, e to the j tau minus e to the negative j tau times e to the minus 3t plus 3 tau. So now, with our exponent bases being the same, we can multiply all of these out, and it adds into the exponent. We're getting 1 over 2j, integral of 0 to t, e to the j tau minus 3t plus 3 tau minus e to the minus j tau minus 3t plus 3 tau.
One thing I want to point out, if I would highly advise you all be very, very careful with your handwriting, because t and tau can look very similar. It's also probably, I think it's also okay if you want to use a different letter than tau, just to make it more clear. But
is it too hard to discern with my handwriting? I know my handwriting isn't the most beautiful, but
no, yours is fine. But
okay.
I know for me, I have that problem, so I don't use tau.
Okay, that is good to know, because if they can't read it, they can't grade it. So just keep that in mind whenever you're doing homework or tests. And if any of y'all are having issues reading my handwriting, let me know and I can switch variables. But just let me know in the chat or speak up now.
I just have a quick question.
Yeah, absolutely.
Can you just explain what you did at the last step where you took out 1 over 2j?
Yeah, so because all of the inside of our integral is all multiplied together, we can treat this all as one term. And this is just a constant, because j is just representing an imaginary number, but it's still a constant even though it's complex. So because it's all multiplication and division, we can just pull the constant out front. if this multiplication sign in the middle was plus instead, it would be a different story. But because everything is multiplication and division, we're able to do that. Does that make sense?
Yeah, so you just distributed it throughout. So for the E, you just
Mhm.
distributed it, I guess.
So I'm not sure I fully understand.
So I'm talking about the last step that you just wrote.
Oh,
Yeah, that
For-
step.
oh,
So I get the part where you take it out. I'm just
Mhm.
confused about that. Where how you went from parentheses to distributing it out. That's what I'm confused about.
oh, gotcha. Okay, I'm sorry. So because we have both terms as e to some value, our base is the same, which means whenever you do multiplication with exponents with the same base, you can just rewrite it as an addition.
Oh,
So you would
okay.
get that. Does that make sense?
Yeah.
Okay. And that was your question this time, right?
Yeah.
Okay, perfect. So yeah, I just took this term and multiplied this, and then took this term and multiplied this. All right. So now we're going to use that same exponent property that I just talked about, but in reverse. So we can rewrite this out as e to the minus 3t times e to the j tau plus 3 tau minus e to the minus 3t times e to the j minus j tau plus 3 tau. And does that make sense based on the explanation I just gave? It's just the same thing in reverse. All right. It looks like we're good. All right. So now we can simplify this again. If we remember that our integral is with respect to tau, which means we can treat our term with t in it as a constant, and we can pull it out front as well. So we can make this e to the minus 3 tau, or 3t, over 2j, integral from 0 to t, e to the j tau plus 3 tau, minus e to the minus j tau plus 3 tau. So now we can integrate this. Actually, I'm going to do one more intermediary step so it's really clear. Sorry, I'm trying to make sure that people can follow my work without being able to hear me as well if people look back at it later. So we can simplify our exponent as tau times j plus 3 minus e to the tau minus j plus 3. And then that makes our integration fairly easy. So we're going to get e to the tau j plus 3 over j plus 3 minus e to the tau negative j plus 3 over negative j plus 3. And we're going to evaluate that at 0 and t, or 0 to t. And please feel free if there's any questions at any point to just speak up. So now we want to multiply each by their complex conjugate to remove the j term from the bottom. So for this first one, we're going to multiply it by negative j plus 3 on both the top and the bottom. Then for the other side, we're going to do the opposite well, we're going to do the same and it looks like the opposite. But we have negative j plus 3. So we're going to multiply by j plus 3 on both the top and the bottom. And now, real quick, I just want to show how you handle this kind of math. So you have to keep in mind that j is representing the imaginary value I, and I squared is going to be equal to negative 1. So in this case, we're going to get negative j squared plus 3j minus 3j plus 9. So these two terms in the middle are going to cancel out. J squared is going to become negative 1 and then cancel with this negative. So we're going to end up with 1 plus 9, which is just going to give us 10. I just want to avoid any questions there, so I'm going to explain it up front. So we're going to get e to the minus 3t over 2j times j plus 3, or sorry, we're going to get negative j plus 3 e to the tau j plus 3 divided by 10 minus j plus 3 e to the tau negative j plus 3 divided by 10 evaluated from 0 to t. And then we can go ahead and we can pull out these 10s on the bottom as well, because it's the same on both terms. So we get e to the negative 3t over 20j times negative j plus 3 e to the power of tau j plus 3 minus j plus 3 e to the tau negative j plus 3 from 0 to t. And now we can go ahead and plug in our 0 and t values. So we're still going to have this out front. So we're going to get negative j plus 3 e to the, sorry. Using tau and t gets me confused myself sometimes. E to the t j plus 3 minus j plus 3 e to the t negative j plus 3. And this is going to be one term. So that's plugging in t. And then we're going to subtract by plugging in 0. So whenever we plug in 0 for tau up here, this term is going to be equal to 1. So we can go ahead and say it's going to be negative j plus 3 minus j plus 3. Does everybody follow up through that step? Okay. And I would recommend, I know I'm taking all these intermediary steps to simplify functions down before I integrate them and stuff like that. I would highly recommend you do that, because it's going to make your life a lot easier in the long run than trying to not simplify, which is just going to be a mess. So once we're at this point, we get e to the minus 3t over 20j times, and then we're going to distribute this out to each term. So we're going to get negative j e to the t j plus 3 plus 3 e to the t j plus 3 minus j e to the t negative j plus 3 plus 3 e to the t negative j plus 3. And then this whole term on the right is going to simplify down to 2j. So now we're going to multiply by our complex conjugate in front to remove the j from the bottom. So we multiply this by negative 20j, both the top and the bottom. And then this term's going to remain unchanged. Actually, I may as well. We're also going to distribute this t and the exponent out. So we're going to get jt plus 3t plus 3e the jt plus 3t minus j e to the minus jt plus 3 plus 3e the minus jt plus 3t plus 2j. So now this bottom term is going to give us, let's see, it's going to be 400 on the bottom. We're going to have a negative 20 on top. So that can be simplified to negative 1 over 20. And then we have our j on top. So we're going to get negative j e to the minus 3t over 20 times everything else. And again, I know this is a very long problem. If you have any questions, please ask, because this is not outside the realm of possibility of being similar to one of your homework questions. Oh, there should be a t here that I missed in the previous step. So now we're going to go ahead and we're going to factor in our term out front. We're going to factor this into everything. And before you do that, I want you to notice that in each term, we have a e to the 3t, and in this term, we have an e to the minus 3t. So those two are actually going to cancel out. So I just want you to be aware of that as I'm going into this. So we're going to get j squared over 20 e to the jt. Again, because the 3t and the minus 3t, both with the e as the base, are going to cancel each other out. Then we're going to get minus 3j.
I was
Yeah.
wondering, where did you get the j squared from again? Oh, did you just distribute it?
Sorry?
So, like for the j squared, did you just distribute it?
Yeah, so we're just distributing this term to each term.
Okay, got it.
So.
Yeah.
And then our negative signs are going to cancel, so that's why there's no negative up there. So we're going to get, for this one, we're going to get 3j over 20 e to the jt plus j squared over 20 e to the minus jt minus 3j over 20 e to the minus jt. And then what is this going to multiply out to? We're going to get, it's going to become minus 2j squared e to the minus 3t over 20, which we are going to rewrite as j squared over 10. All right, now we can simplify our j squared terms. So we're going to say this is, I'm going to say this is negative 1 over 20 e to the jt minus 3j over 20 e to the jt plus forgot the whole point of this step, plus minus 1 over 20 e to the minus jt minus 3j over 20 e to the minus jt. And then this is going to become plus e to the minus 3t over 10. And we're almost there. We're almost done with this problem. So now we can see on the denominator of each of our fractions, we can simplify them a little bit by pulling out a 1 over 10. So we're going to go ahead and do that. We're going to get a 1 over 10.
Wait, I'm sorry. How did you remove the t? Why did you remove the t squared from the last time again?
So the j squared, are you asking about this j squared?
Yes.
Okay. So the j squared is just, j is representing the square root of negative 1. So whenever you square it,
All right.
yeah, you're just going to get negative 1 out, which I canceled the negative 1 with the subtraction sign to get plus e to the minus 3t over 10. Does that make sense?
Right. Yes. Thank
Okay. So now we're going to pull out a 1 over 10. So we're going to get negative 1/2 e to the jt minus 3j over 2 e to the jt plus negative 1/2 e to the minus jt minus 3j over 2 e to the minus jt plus e to the minus 3t. All right, let me make sure I haven't made a mistake so far. All right, this is all I can get. All right. So now we can see we have two terms with a negative 1/2 in front and two terms with a negative 3j over 2 in front. So we're going to go ahead and we're going to group those terms together. And you'll see why in just a moment. So let's go ahead and do negative 1/2 times, actually I'm going to start with the other one. We're going to get negative 3j over 2 times e to the jt minus e to the negative jt. And then we're going to have minus 1/2 times e to the jt minus e to the negative jt.
Would it be plus e to the minus jt? Because like when you distribute it, it's supposed to be like minus.
Let's see. That. This one should be a plus, I believe. Yeah. Thank you. And then you have your last term, e to the minus 3t.
Hey, Ryan, correct me if I'm wrong, but I think in the e to the jt with the minus 3j over t, that I think it should be a plus in there, right? Minus 3j over 2
Yeah, that's
on
the
the
one
left,
I
on the
was
left end,
talking
right?
about.
So term number 2 and term number
Mhm.
4 on the second line from the top.
But because
Mhm.
you're like taking the negative sign out, it's going to be a positive inside for 3j by 2 terms.
I think they're both positive on the inside.
I think that's right.
But positive for this, but I think it's negative for the other
Yeah,
one.
I think I actually had it flipped. I think this one should be negative.
Wait, is
I don't
it?
think so. It's plus
No, no,
minus
it's
1/2, right?
positive for both. It's positive for both.
I think our answer key is wrong then, by the way. Just so you're aware that.
Okay.
But yes, I think you're right. Now that I'm looking at this more closely, I think you are correct. I believe they should both be positive.
Yes, let's go.
But that's going to leave you with a. Sorry, give me just 1 second here. I think I may have made a sign mistake earlier. Because the answer key says this should be a plus up here. So where did I make a sign mistake? Yeah, let's see. You have that. You're multiplying by negative there.
I think you have negative 20j over negative 20j, but then you have a negative j to the on the
For,
outside wall. Simplifying that. Oh wait.
I think that would be fine. But I do have a sign wrong all the way back there. I made a sign mistake somewhere at the beginning that is cascading through this problem.
I think it's just at the bottom line. No, go down, go down. It's just the third step from the bottom.
Yeah, I just changed that because I looked at the answer key and saw that this should be, I had it as minus and it should be a plus. And this should be a plus here too, up here, and then up here. Or rather, this should be a, oh, now I'm really confused. Give me just 1 second. Let me trace back through my answer here.
See, guys, even the TA makes mistakes.
I do
Perfect
make
example.
mistakes.
Perfect example to keep track of your signs.
Oh, I made a mistake here. It's right here. Because it's plus 3, but it's minus. So really this should be a minus sign here if I believe. Is that correct? Does that make sense?
Yeah.
Okay, yeah, we found my mistake. Let that be a lesson. Pay very close attention to your signs.
Wait, sorry, could you go back to the part where you made the mistake? I just need to see.
Yeah, so I made a mistake in this step right here. So when I multiplied this out, it's a positive 3 in here. So I made it a plus down here. But because there's a minus factor here, it should actually be a negative. It should be minus as well. Does that make sense?
Yeah, I see.
We're learning together. Okay, so that's negative. That's negative there. It should also be negative here. We're going to multiply that, and it's going to become positive there, which should fix all of our problems. Positive there, and positive here, which I think is then going to make this a minus. Yeah. Okay, we found the problem. The answer key was not wrong. I made a sign mistake. So whenever you see anything that looks like this or like this in an answer, your mind should immediately jump to Euler's formula. So we went over it up above. So we have sine of t is equal to e to the jt minus e to the minus jt over 2j. And we have cosine of t is equal to e to the jt plus e to the minus jt over 2. So I'm going to go ahead and copy this down. Oh, not cut. Copy that. So now we've got Euler's formula, and we can see this term on the right, this term here, is actually already in the correct form to be a cosine if we just distribute this 1/2 in. But the first term has the top, the coefficient looks like a sine, but the denominator needs a j in it. So we can actually just take this. Generally, you want to move j's from the bottom to the top, but in this particular instance, you can actually multiply by, or wait, you can just multiply by, if we multiply it by just j, it actually will cancel that negative sign. So we can multiply it by just j. This is going to give us j squared, which is going to become -1, and then that's going to cancel with that. And then we're going to go ahead and leave this all the same. Actually, I'm going to go ahead and just factor that into here. Jt plus e to the minus jt over 2 plus e to the minus 3t. So now if you didn't understand what I was talking about before, you can see more clearly now. This term is matching with our Euler's formula definition of cosine. Now we're going to do the same over here. So we're going to get 1/10, or I said the right thing. 1/10. This is going to become 3 over 2j, which we can then go ahead and multiply the denominator into here. And we can go ahead and leave the 3 out front. So we get 3 times e to the jt minus e to the minus jt over 2j minus e to the jt plus e to the minus jt over 2 plus e to the minus 3t. And now the final step, we can arrive at our solution. Simplify this down into 1/10 times 3 sine of t minus cosine of t plus e to the minus 3t. And that is going to be our y of t for our second case. Does anybody have any questions? I know I just did so much math and even made a mistake in the middle of it. So please ask away if you have any questions. Okay, so we have one last step, which is to just finish writing out our solution. So if you remember an hour ago when we were up here, we defined 2 cases. So we should have a piecewise function with two different cases. So for this, we're going to have y of t is equal to, and if you remember, we said for anything t is less than 0, it's going to be 0 because there's no overlap. So we already defined that. Then we're going to come down here and we're going to say our second case was for t is greater than 0. That's the integral we just solved. So we're going to put 1/10 times 3 sine of t minus cosine of t plus e to the minus 3t for t greater than 0. And that would be our final answer. So again, does anybody have any questions? And I also want to ask, did anybody solve this on their own when I introduced it last week? Happen to get the right answer? That would be very impressive.
I worked on it, Ryan, but I didn't get the right answer.
I
I'm
will
joking. I'm joking.
I will leave that to y'all. If y'all got the right answer on your own, congratulations. Okay, if there's no questions, we have one last question that hopefully won't take as long. So I will go ahead and pass it off. Feel free, if you had any other questions, to just drop them in the chat and I'll try to address them. All right, Alpha, are you ready?
Let's go, Will. Let's go, Ryan. Well, thanks, Will and Ryan, for help explaining about the convolution today. I know it's a hard topic. Everyone, I think, is actually the hardest topic for signal and system, but you got this. Got this, everyone. Let's suffer together. All right, let's look at our last problem here. Let me share my screen. Cool. Do you guys see it good? Okay, I don't think I can see the chat right now, but okay. Can you hear me well, everyone?
Yes.
Thank you. Okay, so on this problem tree, we're gonna move on to the block diagram. And there are only 2 steps to do that. To solve the block diagram problem, the first step we want to do is isolate YT. And how are we doing that? Let's see. I'm gonna write down the question that I have right now first. And I want this side to only have YT. Meaning that I'll have to multiply both sides by 3/2, right? Okay, and let's simplify everything. So this chunk is gonna be 12 dyt by dt. If I made mistake in calculation, please let me know, okay? And 9/2 xt minus 3/2 dxt over dt. All right, Now we got the term we want. We isolate yt to be on one side of the equation, like this. I'm gonna save this term for later. Now let's start drawing the block diagram. So the way that I draw the block diagram, I will put xt in this side, and yt, which is the output, is gonna be this side. Let's examine what do we need to do with xt first. So we see our first term here. There's a coefficient in front of xt, right? Which is 9/2. So, because I want to incorporate everything together, I'm gonna set this symbol. To simplify that, I'm gonna add everything together. And on this first term, when we want 9/2 of xt, I'm gonna just draw 9/. I'm gonna write it there, and then pass it to the add sign. And the next thing that we want to look at is minus 3/2 dxt over dt. And the way I used to simplify dxt over dt is that we're just gonna use this block, differentiation block here. And the stuff we will get out of this block is gonna be dxt over dt. But I don't want only this one, right? I want negative 3/2 of dxt over dt. Therefore, I'll multiply that by negative 3/2 in the end. So I'll get negative 3/2 of dxt over dt, right? But just to not get confused, I'm just gonna move this here so we know. And the last part that we want to include is 12 dyt over dt. And how would I do that? I'm gonna do something similar to dxt. I do that by having this differentiation symbol here. And what come out of it is gonna be dyt over dt, right? And there's also coefficient in front of it, which is 12. Therefore, put 12 here. So I get 12 dyt over dt. And then I add everything together. And the last step, I just return that to yt. And our block diagram is just gonna look like this. Simple, just drawing, but still be careful of when you do the isolate yt there. Make sure you do the right calculation. Okay. Anyone has any question on this? Other TAs, do you have anything that you would like to add? Okay, I assume that we are good to move on. Okay. So, okay, I know that today we have like a long convolution and also last week too, problem. Therefore, we have some tips to help you with convolution problem. There can be like main 3 scenarios that you can take into consideration when we want to see if the graph has overlap, some overlap, full overlap, or no overlap at all. So Let's see our first scenario. Oh, I got some chat. Okay, I'll keep it short. Okay, I'll keep it short, everyone. It's been a long day for you all. For scenario 1, we have 2 time-bounded signal. And in the first scenario, it's gonna be no overlap, right? So it's just gonna look something like this. But if we just move our graph like from no overlap and we can move into the next scenario, which is some overlap. However, we want to make a stop here. We don't want to go here or there just yet. We want to make a stop before they're gonna be transition in the graph. You remember the recitation sample from last week? Yeah, it's gonna be like that. So this is gonna be our t. Put t to be less than the time where the shape of the graph started transitioning. So we're gonna stop right there. The next case is gonna be when the graph makes full overlap, which is gonna look like this. And the next case is some overlap, when the graph already passed the full overlap here, right? And move on to another transition. So it used to be positive slope, now it's negative slope. And this is another case that we need to consider. And the last one for this scenario is no overlap at all, which is when the graph already moved past this signal. So it's gonna be like this. And that's for scenario 1. Now let's move to the next scenario. Let's say for this scenario works for one time bounded signal with another time unbounded signal. So I have time bounded signal here. And this is time unbounded signal. The first scenario cause these two start. Okay, this is my origin. So the next scenario is gonna make some overlap, right? So it's gonna look something like this. And the third one is also similar. Whoa. Here, remember our ht minus tau here is actually infinite length rectangular function. Therefore, in the next scenario, full overlap is gonna look like, actually it's gonna look like this here. And you can see on the slide, they state there's like another case which has no overlap, but it's not true for this case, right? Because no matter how much I move it, this rectangle time unbounded signal, there's not gonna be any way it's not overlap. Therefore, disclaimer, be careful. So especially scenario 1 and scenario 2, there can be some exception to it, depends on the nature of signals that you were given. And the last scenario, 2 time unbounded signal. So scenario 1, no overlap. gonna look like this here. This is our origin. Another time unbounded signal, which is exponential decay. Okay, this is the first case. And when I move the graph further, right? It's gonna be some overlap that's gonna take place, right? And it's gonna always be like that because why? We gotta pay attention to the asymptote here. Yeah. And these are just simple demonstration of each scenario that I hope can help you imagine when you do this type of convolution question. Yeah. And that's gonna be all for tonight, everyone. Do you have any question, comment, or concern? No? Oh yeah, we do. Oh, thank you, Nicholas. Oh my God. Thanks for your compliment. It's really, really appreciate that. Thanks for Amelia, Teresa, Will, and Ryan too, for being great TA and help me want to motivate myself to be great TA too. And thank you everyone for joining our recitation session for tonight. I think it's a great time now. And hope you good luck with your class, everyone. Okay, anyone would like to add something? Well, I think we are
Any
pretty
questions,
much
guys?
done for tonight.
See you guys.
Have a good night, everyone.
That was very good, Alpha. Bye.
Thank you, Amelia. Bye, everyone. Have a good night. All right, Rio. Have a good